Hi everyone, we are Team Diffusion. Our project is about creating a more data-efficient model for time series data like ECGs. Diffusion models are growing in popularity. Time series data is critical across many fields, but there's little work on making diffusion models data-efficient for it. Diffusion is now used to upscale images, remove objects, used in tools like Midjourney, DALL-E, and Flux. Diffusion is crucial in generative AI, producing higher quality outputs than GANs or VAEs. But it's still new for 1D time series. It's a two-part process. Noise is added step by step, then reversed by the model to generate realistic data. But it needs massive datasets. Image datasets are huge, while rare ECG datasets are limited. Improving data efficiency means lower compute and data costs. This helps healthcare, finance, and other fields with limited data. Existing methods like augmentation and transfer learning don't work well for 1D. Synthetic generation is a better path. Our goals were to improve data efficiency and test our techniques on ECG datasets to validate them. We prepared our data using filtering, windowing, and pre-processing methods. We first explored Gaussian processes, probabilistic models for function spaces, but they're computationally heavy. Conditional neural processes are more efficient. They learn an implicit kernel and represent distributions. Neural processes, NPs, introduce latent variables for global sampling, but they struggle with real-world ECG noise. They often fail to reconstruct noisy regions or peaks properly, especially in non-Gaussian data. We tested custom loss functions to improve training. None gave significant gains. Attentive neural processes add attention, improving reconstruction and reducing context loss. They model all context points well, especially useful in early training phases. However, ANPs heavily rely on context near peaks. Without nearby context, peaks are missed. Here's how attention works. Queries, keys, and weights are used to aggregate context for predictions. We tested distance-based weights to improve locality, but it hurt generalization and permutation invariance. The final aggregation uses attention and distance together, generating strong representations. We developed a neural diffusion process by plugging ANP into the denoising step of diffusion. We didn't achieve the performance we expected. Here's a high-level diagram of how neural diffusion works with NP components. We then created NeurECG, our final model combining ANP with time-aware embeddings. We used sinusoidal time embeddings, tuned to match ECG rhythms and temporal cycles. This helped encode periodicity and reduced overfitting to nearby context. Here's our CNP-based model adapted for ECG signals. Then we added latent variables for uncertainty modeling. Adding decoder self-attention further improved smoothness and accuracy, especially near context points. This is our final NeurECG model, combining all improvements into one architecture. We can apply it for reconstruction, prediction, denoising, and baseline correction of ECG signals. These are sample reconstructions. Model accurately recovers complex ECG shapes. Here we can see model performance when it generates waves in areas without context points. We also tried generating beyond context points, and it gave good results. Moving to our evaluation process, it compares NeurECG and baseline on large and small datasets. We generate a synthetic dataset and get the accuracies of different combinations of real and synthetic data to get fidelity, diversity, and generalization measures. With only 300 samples, NeurECG outperformed a baseline trained with 40,000. In classification, combining real plus synthetic data from NeurECG improves accuracy significantly for low data scenario. Now let's take a look at our final code. First, we have data loading and pre-processing. Here's some random samples from the data loaded. This is a visualization of the time embeddings. We are loading a previously saved model. Now we can see the reconstructions. Here is the reconstructions with context points taken from either sides. To summarize, we built a diffusion-based generative model that works well even when trained on small ECG datasets. We enhanced it using attention, time embeddings, and self-attention layers. We validated its performance through multiple metrics and practical use cases, and the results were promising. Our research can be extended to improving neural diffusion, optimizing context selection, and real-world deployment like prediction or denoising. That's the end of our video. Thank you.